We are a highly capable species. Really, we're just getting started in an evolutionary sense. If we don't wipe ourselves out, who knows where we're going to go? We are a young species, a vibrant species, a species that has only really just come onto the scene on a planet that's 4.5 billion years old. So we have such incredible potential if we don't mess it up for ourselves.
Dr. Steve Brusatte, what does the history of mammals tell us about ourselves as modern humans?
We are a mammal. Ultimately, we're one of about 6,500 species of mammals today, and we like to think of ourselves as special and unique, and we are. I mean, we absolutely are. Our high intelligence, our consciousness, the civilizations that we built. Of course, we're a special animal, but really we're part of a larger family, the mammal family, that goes back more than 200 million years. The very first mammals lived with the very first dinosaurs. So, when it comes to human history, a lot of us are very interested in human history and studying the world wars and in studying, colonialism and the American Revolution and, going back to the Stone Age and the Bronze Age, fascinating stuff. But really our legacy and our history goes way, 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 way back. And I think there's a lot we can learn about us, about ourselves, about where we came from by looking into that deeper prehistory of mammals. And that's why I've written books like The Rise and Reign of the Mammals to tell that deeper human story.
Yeah. And in your work, what have you found with the development of brains and intelligence?
We are smart. I mean, we know it. We know it. And it's true. Humans have enormous brains. We have especially big brains in relation to our body size. That's one of the key metrics of intelligence if you compare across animal species. Of course, it's very hard to measure intelligence. Just think of all the standardized tests and IQ tests and all these things that humans try to do to see how smart we are relative to each other and how imperfect that is. And it's even harder to measure intelligence across a vast range of animals, from humans to elephants to dolphins to monkeys to squirrels to whatever. But by and large, the bigger brains you have physically, but also the bigger brains you have relative to your body size, those are things that tend to correspond to greater problem-solving skills, greater flexibility, greater adaptability. And we definitely stand out. We do. But mammals as a whole stand out from other animals. On average, mammals have the largest brains relative to body size of any animals today. And some mammals, like dolphins and whales and elephants, have absolutely massive brains. Both in terms of the raw size of those brains. I mean, they're big animals, a lot of those animals, but also compared to body size. So I think the key take home is that, yes, we are smart as humans, but we are part of an intelligent family. And the mammal family, having larger brains, high intelligence, those have been factors that have helped drive and enable the success of mammals over time.
And it must be important, as I understand, the brain size was a big trade-off considering the risk of birth to a baby with such a big head.
Absolutely. And you think about a lot of the issues with childbirth that many mothers have, how difficult childbirth is. I think we tend to take it kind of for granted now. We're just such a technologically advanced society. We have such advanced medical care and so many doctors that specialize in delivering babies, and C-sections can be done on demand and all of this. But in nature, if we were left to our own devices, pregnancy would be so difficult, so much more difficult than it already is for women, because human women give birth to large babies with big heads because of those big brains, and they have to pass through the birth canal, and all kinds of things can go wrong when that happens. This is a particularly human problem because our heads are so big, but it's part of an even larger mammal issue as well, because we didn't evolve out of nowhere. We evolved from apes that generally had large brains that gave birth to large babies. But even more distantly, we had ancestors living probably around the time the dinosaurs went extinct. And this might have helped them survive that extinction. Ancestors that developed the ability to give live birth to bigger babies that develop for many months in the womb of the mother. That's the placental mammal hallmark. That's what we do. Dogs and cats do that. Horses do that. Not all mammals do. Mice don't do that. But placental mammals like us have the capability of giving large birth to babies that develop for a long time inside the mother, inside the safety of the womb. We take that for granted. It is incredibly sublime, unique, sophisticated when you compare to other animals. I mean, birds don't do that. Lizards don't do that. Snakes don't do that. Frogs don't do that. It is really a mammal trademark for a mother to be able to raise a baby inside her own body for that length of time. It is one of our superpowers, and we would not be here today. And in fact, mammals probably could not have even taken over from the dinosaurs if they did not have that ability to give birth to bigger babies.
Mm-hmm. And then mammals, mammary glands. What impact does the milk then also have on brain development?
Milk is another thing. We take it for granted. Either, as parents, if you're a mother, feeding your baby, it's just kind of normal. It's what your body does. Even just living our everyday lives, most of us probably drink milk that we buy at the store, milk that's come from cows or baby goats or sheep. But it's just absolutely normal for us. But birds don't drink milk. Lizards don't drink milk. Frogs don't drink milk. This is a mammal thing. And mammals have this ability, mammal mothers, to provide this nutritious, sustainable substance that they make in their own bodies to their offspring. And that's another superpower, really, because if you think about, let's say, a bird, birds are warm-blooded like us. They have big brains like us. But bird parents have to go out and get food for their babies. And if the weather's bad, if it's cold, if there's been a drought, there might not be much food out there. That's a problem. Mammal mothers can make that food themselves. So we think, in an evolutionary sense, that the evolution of milk mammary glands was integral to the evolution of bigger brains. And you see them roughly correspond when we look at the fossil record of mammals, when we look at what mammals were doing like 200 million years ago. We can see when the brains were getting bigger. We can look inside their heads, CAT scan the fossil skulls of mammals, see the brain cavity getting bigger and bigger. But there's then also a telltale sign in our teeth whether we're drinking milk or not. And that is whether there's one set of baby teeth, one set of adult teeth. That all has to do with drinking milk. That's highly unusual. Most animals that have teeth, whether a shark or a crocodile or a lizard, they're constantly growing new teeth, losing teeth, breaking teeth, replacing teeth. Mammals don't do that. And it's all because of drinking milk as babies. Early on, when our jaws are developing, we have the milk from our mothers. We don't need to chew. So we get this set of baby teeth that's imprecise. And then when our jaws are basically full size, we can get the adult teeth in. And we only have one set of adult teeth because our teeth, can bite down so strongly. We have molar teeth and premolar teeth and incisors, all these different teeth that correspond, the upper and lower jaws. To get that precise correspondence for the teeth to interlock, you can't just be growing them throughout your life. You can't just be replacing them anytime they break. You basically have to get one final set of teeth. So all of this stuff is linked. I know I'm breezing through a lot of anatomy, but these are all things that are just fundamental to us. We, as an adult, if we break a tooth, that's it. It's done. We got to go to the dentist and get a replacement. As kids, we lose teeth. As kids, we drink milk. Throughout our lives, many of us drink milk. We have big brains, high intelligence. All these things are things that came from our distant mammal ancestors, and they all evolved in concert with each other. And they work together to make those ancestors more adaptable, to help them survive over vast stretches of time when climate was changing and asteroids were raining down. But of course, today, all of those things that are integral to our own humanity are seen in other mammals, and they're all part of that survival toolkit that makes mammals so successful today, hundreds of millions of years after the first mammals entered the scene.
Yeah. So the teeth thing is interesting. It seems so integral to your work, having records of teeth and things.
Yeah.
And wouldn't it be nice if we could maybe, keep the fit, but then a tooth falls out, but then one grows in that fits perfectly? I seem sort of envious of animals that have all these teeth.
I know. And, a T-Rex was like that, for instance. It replaced its teeth throughout its life, as did other dinosaurs, and as do, almost all animals today that have teeth. But in most animals that have teeth, They just have a bunch of teeth. Usually they look basically the same throughout the jaw. You don't get different types of teeth that we do, ones that grind, ones that slice, ones that grab. That's, this is classic mammal set of teeth. And also those teeth in say a lizard or a frog or a T-Rex or a shark, they're just all kind of chomping down. They're not precisely interlocking with each other like puzzle pieces when the upper and lower jaws close. That means that most animals can't actually chew. Chewing is another thing that we take for granted. Obviously we chew our food, but that's pretty unusual. A T-Rex did not chew its food. Sharks don't chew their food. They just bite and slash and cut and swallow. So I think we're starting to see that many of the things that are so normal for us are actually highly unique among animals, and they're not human features. They all shape our biology and our behavior, but they're not human features, they're mammal features, and we inherited them from our distant ancestors. And we have fossils showing how that happened, which, as a paleontologist, that's what I find particularly cool.
Yeah. So when you're looking at things like this, do you see in fossils maybe a record of some phase where that trait was starting to show and maybe some had it and some didn't? If they don't have it, are they not yet mammals? How do you look at that?
Yeah, that's a great question. And so, yes, you can see that all these things we've been talking about, they didn't all evolve at the same time. A lot of these things were related to each other. But, the milk probably came before the really big brains, for instance. But it's hard to tell because with fossils, we're dealing with little clues, little snippets of evidence. If we're kind of like detectives, paleontologists, and we're dealing with the clues that we can find, not the entire picture, not the entire crime. We weren't there to witness it all. So we have to piece together with the clues. So maybe we have one fossil here and one fossil there. And maybe this is a fossil skull, but this is only a few teeth, but this one is a backbone. And, so you have to piece it together. And over, tens, hundreds of millions of years, you're going to have gaps in that record. So it is hard to tell sometimes what came first or what drove what. But when you say, what makes a mammal, this kind of gets into the weeds because it becomes a little bit subjective, because all these things we've been talking about are all mammal hallmarks. So really when scientists are naming things, that's a human exercise of classifying the names we put on things. And so it just so happened that quite long ago, anatomists, people that were studying the bones of not, just fossils, but of modern species, decided on this definition that, the dividing line between true mammals and their more primitive ancestors and cousins is that true mammals have a single jawbone, like we do. Kind of arbitrary to pin the definition on that, but it's one that's pretty straightforward. All mammals have a single jawbone. The ancestors and cousins of mammals had lots of bones in the jaw. Our single jawbone is quite important because that's linked to the different types of teeth that we have, and having these different teeth that can bite together so strongly and interlock so well and chew food, you really need a single jawbone to do that well. A single simple bone, all the teeth on those bones, the muscles attaching to those bones, a simple kind of puppeteering system to make those bites strong and to orchestrate that chewing. And of course, as we've been talking about, being able to chew your food, having the one set of baby teeth, one set of adult teeth, that has to do with milk and it has to do with bigger brain. So that single jawbone, as maybe arbitrary or as meager or as kind of random as it seems, why pin the definition of mammals on that? It actually turns out to be quite important. And I should then also say that it had repercussions, because our mammal ancestors, what they were doing was they didn't know that 200 million years in the future, some mammal descendant scientists would be pinning names on things. All they were doing was adapting to their world. And what they were doing was they were simplifying their jaws so that they could bite harder and bite stronger, basically. And they were developing that system of feeding their babies milk and having the baby teeth and then replacing them with a set of nice, strong, interlocking adult teeth. That's what they were doing. As they did that, that meant that they had all these redundant bones in their jaws, and you see this today in a crocodile, in a lizard. If you look at a T-Rex skeleton, they all got a bunch of bones behind the part of their jaws with teeth. So our mammal ancestors, as they were simplifying their jaws, They lost some of those bones, but some of the other bones in the back of the jaw, they repurposed those bones. They changed those bones. They moved those bones. Those bones got small and they migrated from the jaw into the ears. And so we have these 3 tiny little bones in our ears. All mammals have them. The smallest bones in our body. They're like the size of a grain of rice, each of them. I mean, absolutely quirky bones, the kind of thing you get in, a Trivial Pursuit game or a pub quiz. What are the smallest bones in the body? The 3 ear bones. 2 of those bones come from this repurposed lower jaw bones. They're the same bones that are in the jaws of our ancestors. When we are babies in the womb and we start to grow, those bones actually start in our jaws, and then they get smaller and they migrate. And you can watch that day by day in a human developing fetus, which is fascinating. And then in adults like us, well, one of the reasons we're able to hear each other so well is that mammals have good hearing compared to other animals. Why is that? Because those bones in the jaw that were in the jaw that moved into the ear, they amplify sound. They help us hear better. They're kind of like a chain of bones, almost like a chain of megaphones. You line up the megaphones and whoop, the sound is much stronger. So there's another quirk of our anatomy we might not think much about, but it's integral to being a mammal. We have it. The way that our whole sensory system works, being able to hear well, is all because of those bones that are in our ear that were once part of our jaws.
And this jaw thing too, it also helps us to be able to hear when we're doing things like chewing, so we can have a conversation while we're eating.
Yeah, absolutely. So, for those of us that were, scolded when we were young, don't talk when you're eating, the whole reason we can kind of have a conversation while we're chewing is because, our jaws can do that chewing, and those bones in the ear amplify sound. And there's actually even another special bone that's more, it's not like a new bone. It's like a modification of some of the skull bones of our ancestors. It's called the bulla. And it's almost like a bubble of bone, but it's very strong. It looks like a bubble, but it surrounds part of the ear. It surrounds those inner ear bones, and it's like a noise-canceling headphones. So we have like noise-canceling headphones in our head that helps us hear sound better, and that means that when we do chew and our jaws are moving, or with plenty of other it comes in handy all the time, just if there's a lot of ambient noise in the environment or whatever. But that's another mammal hallmark. Dinosaurs didn't have that. Lizards and birds and so on today don't have that, but mammals do.
Yeah. Back to milk and brains for a second. We talked about how it allows the brain to be bigger. Does it also have something to do with the sophistication of our brains?
That's a good question, and I don't know the answer to that. I'm not sure. I'm not a great expert on brains, although we're doing a lot of work on brains in my lab, and myself and my students and some of our colleagues. We are studying a lot about how brains changed over time using what we see in fossils. What it comes down to it in fossils, we don't normally get fossilized brains. Brains are some of the softest, most supple parts of our body, and they decay away so quickly. So to preserve something like that as a fossil for millions of years it's not impossible. You don't want to say it's impossible, but there's only been a few instances ever where somebody's found or claimed to have found fossil brain tissue. But what we do have in fossils is we have the space where the brain once was, the brain cavity. So if you found a fossil human skull, you'd have this big old empty space in here. The brain wouldn't be fossilized, but the space is there. You could CAT scan that skull. You could use computer software simply to just digitally fill in that space, and that would give you a digital cast of the brain. And you can measure that. You could see how big it is, how deep it is, the volume of it. And you might be able to get some clarity on the different regions, the cerebrum, the cerebellum, the olfactory bulbs that control smell, the optic lobes that help with vision, and so on. But a lot of times in fossils, we don't have that sort of detail. We might only have the brain cavity, and that's all we can really work with. So it makes it very hard to know for sure whether the elaboration of different parts of the brain had anything to do with milk. We just don't have much evidence there. But one thing that we do know is that mammals do have this special aspect of their brains, our brains, It's called the neocortex. That's that big folded convoluted part of our brain, basically the stuff that covers the rest of the brain. Inside, it's 6 layers of tissue. And it basically is part of the cerebrum that has just grown big and engulfed much of the rest of the brain. And it does so many things, the neocortex, but is especially involved in sensory integration. So for linking together information from different senses. Only mammals have a neocortex. We can see in fossils, usually if it was there, because it leaves a distinctive mark on the inside of the skull, if you have this expanded bit. And best we can tell, that neocortex was there quite early in mammal evolution, around the time that milk was probably evolving. So I think it's quite reasonable to link those two. It's just hard to really prove it or test it, very rigorously.
Yeah. So we have this huge brain, and then we've got to be born through hips.
Mm-hmm.
And at the same time, we are these creatures that are bipedal and upright walking from our hips. So bipedal upright walking must be important. What is it?
Well, it certainly is for humanity and for the evolution of humans. It was really key. It also explains a lot of some of our neuroses and some of our problems walking upright. More physical neuroses than others, but and it's unique. It is really, really, really for mammals. We're basically the only ones that do it. There's some other apes that can walk a little bit bipedally at times, and there's some fossil apes that could. There's even some that maybe could do it in the branches in the trees when they were still in the trees. But if you think about other mammals, walking bipedally, no. I mean, it was Plato. I think it was Plato. I'm pretty sure it was Plato. Sometimes I mix up my ancient Greeks. Could have been Aristotle, but who defined humans as featherless bipeds. That was his definition. And what he basically meant by that is, we're the only mammals that do this. Birds are really the only other animals around today that, they just walk on their hind legs. And pretty much everything else, whether it's a lizard, a frog, a salamander, crocodile, whatever, walks on all fours. Now, we know from the fossil record that there were dinosaurs that walked on only their hind legs, like T-Rex and Velociraptor, but those were the ancestors of birds. That's where birds got their bipedalism. So we are pretty unusual in walking only on our hind legs. This is something that humans started to do probably 5 or 6 million years ago as our ape ancestors came down from the trees. And this happened in Africa. It probably happened as local climates were changing. There's a lot of stories about the climate was getting drier and the forests were drying up and the landscape was opening and the apes had to come down from the trees. Those are probably a little bit, just so stories, like something Kipling would write, not really something that, we can rigorously test, but probably there were some changes happening in the environment. There probably were fewer forests, more open land, and there was probably just this open ecological niche for some of these apes to fill if they could come down from the trees. And that's what our ancestors did. It looks like from fossils that some of these apes were, again, like they were living in the trees, but they were standing pretty upright as they were navigating the branches. So they were almost like walking on the branches, like a hybrid lifestyle. And that, if they were doing so, and it seems they were evolving that not in order to one day move on to the land. That's not how evolution works. They were evolving that ability because it must have helped them in the trees. It must have been adaptive in the trees, whether it helped them climb trees better or navigate better or more safely, or if it had to do with, a lot of them were probably fruit eaters with balancing and reaching fruit. You can make up all kinds of stories, but the fact is that some of these ape ancestors of ours were starting to stand more upright and walk along branches when they were still living in the trees. Then some of them came down from the trees and really settled the open land, and they were bipedal first, and before many of the other major changes that, made them into the humans that we are today. So being bipedal, that happened before our brains really ballooned in size. Mm-hmm. It was probably linked. I mean, being able to only walk on your hind legs having your hands free to do other stuff, to build tools, to harness fire, to hunt better. I mean, that would probably enable us, our ancestors, to have taken in more calories that could have gone to a bit bigger brain. I mean, it might not have been as simple as that, but probably that was part of the process. And in that sense, being bipedal is so central to being human, but it does explain some of our problems, especially things like back problems. I mean, most animals are not going to have back problems. So many of us do because, our spine and our ancestors was horizontal to the ground, and now we've gone upright, and this upright spine, it means that our spine's always being compressed by gravity, and that's not good. And so, a lot of the pain that we have, back pain, muscle pain, joint
Yeah.
pain, has to do with walking upright. But I guess that's the trade-off for evolving this new way of standing that probably helped trigger our even bigger brains and our tool making and our harnessing of fire and eventually our culture.
Yeah. And you talked a little bit about maybe being able to take in more food. It seems a lot of this is about food scarcity too. And again, back to evolutions in the jaw and things to be able to eat what we breathe and stuff like that. How important was food scarcity for mammals?
I don't know if it's so much scarcity as just evolution is like the Red Queen in Alice in Wonderland. You're always running to stand still, and you're always, as an organism, having to deal with whatever the whims are of the moment, whether it's pressure from other organisms, whether it's the climate, the environment. And for all animals need food. So really anything that can allow them to eat more or have more sustainable food or more regular food is surely going to be favored by natural selection. And especially for mammals, we are warm-blooded. That developed somewhere in our evolutionary history is not quite clear. It's not like a switch was just flipped one day and some cold-blooded ancestor became warm-blooded. There would have been a transition. But being warm-blooded means we need a whole lot more food than other animals. It's something like, we need like 8 or 9 times, I can't remember the exact number, but it's something in that ballpark, 8 or 9 times the amount of food than a cold-blooded animal of similar body size, just to power this internal furnace of ours where we have a high body temperature that's constant, that's controlled internally, an internal furnace. And it doesn't matter if it's the dead of winter, it doesn't matter if it's the morning, it doesn't matter if you're in the shade, your furnace is always burning hot and is always steady. And to have that sort of fine-tuned metabolism, you need a lot of energy. And just like you have to feed a furnace gas or coal or whatever it is, we need to feed our internal metabolism a lot of food. So anything that can help mammals or birds, the same birds are warm-blooded, get more food is probably going to be extra beneficial to us. It's important for crocodiles and lizards and frogs and so on as well. Of course, they got to eat. But being cold-blooded, having slower metabolisms, it's not going to be as detrimental to them if, 1 week the weather's bad or something like that. For us, that could be the difference between life and death. So I think you're absolutely right. A lot of mammal history has had to do with food and in procuring food.
Okay, so right now we live in a time where most people, at least in America, are obese. Are we on the brink of something awesome because we've got this excess of calories? Can we do something great with it?
Oh, wow. See, now you're getting into some trippy things that I will profess my ignorance. So I love looking into the past. I can tell you what's happened in the past. I can inform on maybe what's happening now. Looking into the future. Oh, most paleontologists hate to do this. You're absolutely right about obesity, of course, which is a product just of our lifestyles. We evolved from these apes that came down from the trees that were basically, endurance runners, that were ground animals. And there have been estimates of this, and I can't remember the numbers off the top of my head, but, I think even like, hunter-gatherer groups of humans in nature, in kind of natural settings, up until quite recent times, we'll walk 15, 20 miles a day. I mean, just looking for food, just foraging. So that biologically and physiologically, that's the type of lifestyle we evolved to lead. And it's only really been in the last 10,000 years or so, like with the advent of agriculture and then you got more settled cities and more sedentary populations and divisions of labor, between people doing different jobs. And a lot of us, me included, unless I'm out looking for fossils, I mean, I'm basically sitting at the desk, writing, looking at emails, developing my lectures. So that explains in large part, the obesity issue, that, and of course all the, processed food that's marketed to us and stuff. But whether, we put those extra calories to use, I don't know. They're not going to our brains, they're going to our midsection. Yeah. And I think, that evolution, maybe over the course of like many thousands of years and many thousands of generations, maybe, if we got used to this high calorie diet and sedentary lifestyle, maybe natural selection would catch up, maybe. But it takes natural selection so long to do that. And the changes that are happening with things like our diet, these things are happening over the course of decades and stuff. And so, who knows? But these are fun things to just think about, making the link between, how humans are living today and where we came from. And ultimately, there's just a huge disconnect between the way most of us live our lifestyles today and what our ancestors in nature, proper, true humans, I'm not talking about ancient apes, or actual Homo sapiens, were doing, just 10 or 20,000 years ago.
Yeah. What would you want us to evolve if this calorie surplus could give us extra features?
I wanted to go to our brains and, I don't know, maybe create some kind of empathy lobe or something to keep us from being at each other's throats all the time. And some like lobe of the brain that would help us see through BS and misinformation and online radicalization and all the stuff that tears us apart. That's what I would hope, but I think that's probably wishful thinking. Evolution, can't work towards end goals like that. So, for those of us that want those things, we probably have to start thinking about that other very human tendency to pray for it, some kind of higher power.
Yeah. Okay. So you say evolution can't move us toward that, and yet we seem to be particularly social animals. Mm-hmm. Have we evolved to be so social, or is that something that is just kind of a mammal thing in general, or is that unique to humans?
Yeah, great question. And I'll say, once we really get into human evolution and human, especially cultural evolution, this is not really my expertise. So what I know about this stuff is what I read. I could be wrong. But my broader perspective is where humans came from among mammals. And yeah, many mammals are social. Many mammals, of course, have a strong bond between parents and offspring, especially mother and offspring. And those bonds mean something. There's even a whole hypothesis about why mammal brains are so big and why some mammals have particularly big brains, and that being due, at least in part, to sociality, to living together and communicating with each other and signaling to each other, displaying to each other, just living in, complex relationships with other members of the same species. With humans, I don't know. There are a lot of theories out there about how human civilizations developed and the evolutionary benefits of that and so on. Not my specialty. I don't, the cultural anthropologists, they study this stuff the same way I study the fossils. And so, I don't want to speak out of turn for something I don't know. But I guess what I would say is that when I look at myself, I don't have sharp teeth. I don't have claws. I don't have armor. But I, do have a big brain like all other humans do. And I do have social networks with my family, with my friends and the workplace and so on. So I think for a species like us that doesn't really have, offensive weapons in our, on our bodies and doesn't have, armor to protect us and so on, being social is very important. And even if it didn't evolve that way, it's definitely, the case now that being social is just integral to being humans. And really, we rise and fall based on our collective societies now.
Yeah. And Steve, you said we're featherless bipeds. So we don't have feathers. We do have hair.
Yeah.
What is it about hair and mammals?
Your hair is a lot nicer than mine. Mine's going. But yeah, I mean, hair is a mammal thing. And I won't cease being one when I finally lose all my hair. That's not how evolution works. I once had hair. My ancestors had hair. So, and that's just to be, because we do, I say that actually kind of being funny, but sometimes we actually do get that, students will ask me this in all earnestness, a snake doesn't have legs anymore, so how can you call it a reptile or whatever? If your ancestors had something and you lose it, you're still a member of the group. An ostrich can't fly, but his ancestors could. It's still a bird. So anyway, that's totally a tangent that came from me making an awkward bald joke, but at least is at my own expense. Anyway,
I like
hair,
it.
yes, very mammalian. Nothing else has hair. No frog or salamander or lizard or snake or crocodile has hair. Birds have feathers. Birds, of course, use their feathers to fly, but birds also use their feathers for lots of other things, to display to rivals, to attract mates, to keep themselves warm. And we know from dinosaurs, and actually I study dinosaurs a lot more than I study mammals. We know from dinosaurs that a lot of dinosaurs had feathers, and those feathers dinosaurs had were simpler feathers for the most part than birds have today, and they were the evolutionary precursors to the flight feathers of birds, and that these dinosaur feathers actually started out as things that looked a lot like hair, just little strands that coated the bodies of these dinosaurs. And the stuff was not hair. It was made up of different chemical structure, but quite similar. So hair, full-on bona fide hair, is unique to mammals, but dinosaurs and then birds, evolved the similar thing in terms of feathers. Probably no coincidence that dinosaurs / birds and mammals are the two great groups of warm-blooded animals today. And so this hair, or the feathers, they both grow out of the skin. They're integumentary structures that grow out of the skin. And they probably first evolved to help regulate body temperature as the early mammals were becoming warm-blooded and as the early dinosaurs were becoming warm-blooded. And it's not so much like keeping the body warm. I mean, hair and feathers will do that. They will act as a coat of insulation if it's cold. But of course, animals aren't always cold. So why would you have hair in the summer times? It's more about regulating body temperature, controlling body temperature, being part of that repertoire of keeping body temperature high and constant. And so the hair and the feathers are really kind of like, the windows or whatever. If your furnace is going full blast, you want the walls and the windows of your house to be working. They help keep it contained. And that's probably what, hair and feathers evolved for. Of course, then in dinosaurs, some of those dinosaurs took those feathers, elaborated them into this totally new structure, these quill pens that lined up on the arm that could be used for flying. Mammals haven't quite done that. We haven't modified hair in any super crazy, outlandish way, other than humans, of course, and all the things we do with our hair. But we could in the future. Who's to say, 100 million years from now, some bat or some kind of small, mammal living in the trees doesn't elaborate hair into big, broad surfaces for flying, like birds did.
Mm-hmm. And Steve, you work on the Jurassic World movies as well.
Yeah.
What about dinosaurs with hair with feathers rather in the movies? Will we see it?
Yeah. So one of the great perks of my job is I get to work on the Jurassic films. I've been the paleontology consultant on the last two ones, on Dominion, which came out in 2022, and then Rebirth, which just came out this last summer, summer of 2025. And, the only reason I was invited to do it is quite random. It's the director of the previous film, Colin Trevorrow. He read my book on dinosaurs. He read The Rise and Fall of the Dinosaurs, which is the precursor to the Rise and Reign of the Mammals book we've mostly been talking about. But Colin read the book, and he was starting to work on the next film, and he just reached out. He said our former paleontology consultant retired. That was a very eminent paleontologist named Jack Horner, who discovered the first dinosaur nesting grounds, very eminent guy in our field, but he retired, so they needed somebody new. Colin read my book, had a chat. He came to Edinburgh. I went to the arts festival, the Fringe Festival, and, we sat down, went to the Scotch Malt Whiskey Society, but it was noon, so we had coffee, very good coffee, and we talked about dinosaurs for about, 2 or 3 hours, and he said, "You want to come on board to work on the films?" And I said, "Hell yeah, this is, this is living the dream. Are you kidding me?" And and then one of the first things he said was, all right, I want feathers on some of these dinosaurs. We haven't had feathers yet in the movies. I want them to happen in this one. The reason that they didn't have feathers in the first few films is actually, it's really simple, and it's really actually quite boring. It's kind of a dull reason. It's because the first feathered dinosaur fossils were not found until 1996, which was 3 years after Jurassic Park came out as a film. So there was plenty of evidence back, when the film came out, that today's birds evolved from dinosaurs. They talk about that in the film. I mean, they talk about how bird-like many dinosaurs are, how smart they were, the raptor dinosaurs, but nobody had ever found fossilized feathers on a dinosaur because it's super hard to find a fossil feather, because feathers are soft and they decay away quite quickly. And that's true of most soft tissue. Hair, very few fossil mammals have hair preserved. That's because it decays away quickly. Skin, internal organs, that kind of stuff. Usually it's the bones, the teeth, the shells, the hard parts that get turned into fossils. But in China, it just so happened that in the Cretaceous period, about 125 million years ago, there were these entire ecosystems, these lush forests that were full of not just dinosaurs, but mammals and pterodactyls and crocodiles and all kinds of things. They were buried by volcanoes, almost like Pompeii when Mount Vesuvius erupted. And the volcanoes just killed a lot of stuff at once, quite tragic, but they locked everything in. So, they captured those dinosaurs like a freeze frame, and the feathers didn't have time to decay, so they were preserved. And a lot of the mammals there are found with hair for the same reason, fossil hair. It wasn't until 1996 that it was farmers actually in northeastern China that found these fossils out working their field. And then that instigated, that triggered this gold rush, basically, this fossil rush. And now we have thousands of fossils of these feather-covered dinosaurs, but it wasn't until the mid-90s that they were known. So Jurassic Park came out in 1993. Those raptors became icons. They established a brand identity, not just the films, but the toys and the theme park rides and everything. So, of course, it, would have been very hard to just change those velociraptors or the T-Rex or any of the other dinosaurs. But Colin wanted to add some new characters. He brought some new dinosaurs into the film. And in particular, there's this one called Pyroraptor, which in the film, it's shown as like a golden retriever-sized creature with just these bombastic feathers, wings on its arms, all in this, fiery red color. The color, we don't know if that's true, but it did have feathers like that. It absolutely had feathers and wings like that. We know that from real fossils.
Yeah. So in this long story, we have humans as this featherless biped with a big brain. How much of mammals and the time span of mammals really do humans take up?
Absolutely tiny, minuscule amount. So mammals, our mammal ancestors go back like 325 million years. That's when the mammal ancestors split off from the reptile ancestors. Now, those first mammal ancestors would have looked nothing like mammals today. They would have looked like little lizards, but they were our distant ancestors. The first things that really looked like proper little mammals with fur would have been around when the first dinosaurs were around, about 230 million years ago or so. So you can think of the evolutionary history of mammals as about 230 million years long. It was only 5 or 6 million years ago that some apes came down from the trees. And it was only about 300,000 years ago when Homo sapiens entered the scene in Africa. So 230 million years, 300,000 years of Homo sapiens is absolutely minuscule. So we are just really a hiccup of mammal history.
Mm-hmm. So if the story isn't all about humans, what have we done that you think is unique among mammals?
Yeah. The history of mammals is not just a history of us. It's not all about us. Evolution doesn't work that way. It's not like there was some grand designer, millions of years ago that flipped some switch and said, one day there will be human beings that evolve. Now, of course, there's room for our own spiritual interpretations on things. I'm not, plenty of room for that. But what we know from fossils is that there was a physical process of evolution that's taken really billions of years in terms of Earth history. And nothing is really preordained in that sense, at least with the physical bodies of things and how things physically change as environments change. It's really up to happenstance and what's happening in the here and now as organisms adapt to their environment. So the story of mammals isn't just some long backstory that leads to us, but that doesn't mean that we're not interesting, that we're not sublime and spectacular. We are. I mean, we are mammals. We have hair and feed our babies milk and, have molar teeth and chew our food and have those ear bones that amplify sound, and we walk upright and, all the things that mammals, do. And then we've gone a bit beyond that with walking only on our, our hind legs and so on. But really, it's our brains. It's our brains and what we do with our brains. It's just the high levels of intelligence. It's consciousness. It's the language abilities that we have that are just so far eclipse any other animals that we know. And it's, the ability to work in groups to solve problems. And this has been there from, very early in mammal history. In part, big brains go way back in mammals. Group living, links between parents and offspring go way back in mammals. But humans have really built on a lot of that. They've elaborated a lot of that. And early in human history, you have evidence of not even Homo sapiens, some precursor species. Making boats, getting to islands, traversing the water. These were not Homo sapiens. These were things like Homo erectus, some of our close relatives that ended up on islands in the Philippines and Indonesia. The only way they could have got there is if they had boats, as far as we know. And it's not like it just happened once, it happened many times. So if that's true, and there isn't something that we're missing, these early human species already, they must have had very complex social relationships. They must have been very good at working together. They must have had some kind of language in order to coordinate, to do things like, build a boat. So these are the things early in the human lineage that are starting to really, truly be special and truly be, distinctive, and the spark of humanity. And then later, of course, comes art and seeing art on cave walls and this life of the mind that we have. And making jewelry and burying our dead and, all the spiritual things that we do. So, most of that is very recent, though, very, very, very recent in the history of mammals. And that, I think, is what sets us apart. And it's the source of a lot of the destructive things that we do, but it also is what gives me hope that, we are very intelligent. We have consciousness. We can see and understand the world around us. We can see how we affect the planet. We can grasp how we affect each other. We can make plans. We can carry those plans through. We are a highly capable species. And, really, we're just getting started in an evolutionary sense. If we don't wipe ourselves out, who knows where we're going to go? We are a young species, a vibrant species, a species that has only really just come onto the scene on a planet that's 4.5 billion years old. So we have such incredible potential if we don't mess it up for ourselves.
Yeah. You mentioned our consciousness. What does that mean to you?
So I am not a cognitive biologist or an expert on brains or anything. So this is where I'll show my ignorance right away, and apologies to anybody who's listening who actually studies, human psychology and human sociology and human consciousness. But for me, it just means being aware of our surroundings, being aware of cause and effect, being aware of how we affect each other, how we affect the environment, just having that knowledge about self, both as individuals, but also as a species. And I'm not saying that other animals, don't do any of that ever. There's plenty of little, glimpses of that in other animals, I know. But for me, that's what stands out, in human consciousness. When I look at even the very smartest mammals, next to us, things like dolphins and whales and stuff, great abilities to do things, to problem solve. They have, forms of language, They can even do vast, incredible things we can't do, like echolocate. Some of them, have a sixth sense, but they don't have that self-awareness that we do, at least in the same way that we do. And again, apologies to anybody who actually knows this stuff, but that's what stands out to me, just comparing, myself and other humans to other animals.
Yeah. Well, to keep it within your field, what evidence in the fossil record and things that you look at shows that we developed to that moment? Is there a dividing line?
I don't think there is a dividing line. And again, this is getting out of my expertise, but certainly this is where you go from paleontology into archaeology, where you go from the fossil record, where, you're looking at bones and teeth and skeletons, footprints, humans did leave footprints behind, those sort of physical evidence, the same sort of things you could find for a dinosaur or a woolly mammoth. You go from that to the archaeological record, where it's a record of humans doing things and building things and painting things and drawing things and carving things and burying things and so on. That's really where my expertise stops. What I do know is when I was writing, the Rise and Reign of the Mammals, I did a chapter on humans, and it was the chapter I dreaded the most, just because it's a whole different field of study than my own, really. And it's about us. And of course, we're all very sensitive about ourselves. And I don't want to get anything wrong about us. And you're entering different domains once you get into modern humanity. So I really dreaded writing it. But in the end, I enjoyed it because I learned a lot about the fossil record of humans. And I learned a lot about how our understanding of human evolution has changed dramatically over the last few decades. And it used to be, up until, 2000, 2010, even from what I recall in the literature, you would see, a lot of this work saying that, there was some spark, that something just happened very quickly and the human brain kind of, exponentially went up a scale. And there was this great cognitive revolution. You see that story in books like Sapiens, that do try to cover the broad sweep of everything. And that's the risk when you're trying to do a big history like that. When you go from the animal side of evolution to modern humans, it's just very different. But from what I understand now, there's a lot more evidence that there wasn't just some cognitive revolution, that there were, different bands of humans, different groups of humans across Africa at different times over, a few tens of thousands of years, probably maybe over 100,000 years, that were just learning new things here and there. And they were transmitting those things to other people, and they were learning from each other. And, almost like through trade networks or just, little relationships, just meeting members of the other bands and stuff. And some things would develop multiple times, the drawing on a cave wall or something like that. And it was just a lot of experimentation early on, not just one big bang where all humans suddenly became really smart. But then a lot of that coalesced as those different bands of humans met each other and interacted. And then as the climate changed and allowed, some of those humans to migrate out of Africa into Europe, into Asia, they confronted new challenges. They met older species of humans that had gotten out of Africa before, like Neanderthals, and that cultural evolution, continued and went into overdrive. That's my understanding of it. Apologies to the paleoanthropologists and especially the cultural anthropologists that study these things. But I think the key thing that I learned, which I think is still true, is that there wasn't some big bang cognitive revolution where humans went from like an animal to modern day humans just, in a generation or something. It was something that did develop over time. But in the grand scheme of Earth history, again, 4.5 billion years of Earth history, it wasn't a whole lot of time where humans went from, an ape coming down from the trees into an animal with an enormous brain, with self-consciousness, with the ability to, form civilizations. And I think that's pretty fascinating.
Yeah. And in your book too, you have a narrative kind of, I think, from the perspective of a woolly mammoth about a run-in with the humans. And then, as it's taken down by a hunting band, it has this sort of recognition like this predator is different.
Yeah.
What's different in our hunting and things like that?
Yeah. So I'm not a fiction writer. I could never do a novel. I could never carry it more than a few pages. But in these books, I do occasionally like to do kind
Yeah.
of like the 3 or 4 pages that I think is my limit of fiction storytelling. Just imagining, what a scene might have been at a particular period of time. I've done it with dinosaurs. My next book's on birds, by the way, that'll come out next year. And so I've, done this with stories, different times of bird evolution. But in the mammal book, I did one of these stories about just, a few tens of thousands of years ago, uh, in the part of the country where I grew up. I'm from Illinois. I'm from northern Illinois, outside of Chicago suburbs, out in farm country. And that's really glacial country. This was the area that was just covered by glaciers in the last ice age. The land was scoured down. And I'm imagining, this woolly mammoth that's living in that area, that the ice cap is not far away. It's basically where Chicago is now. Lake Michigan is actually glacial meltwater. That is the melted remnants of the glaciers. They did not leave that long ago. But I'm imagining this mammoth, and the ice cap is in the distance. The wind is, rushing down, and the mammoth is seeking shelter from a storm, and these hunters come out and confront it, but they're unlike anything it's ever seen. They're not saber-toothed tigers. They're not dire wolves. They're not, creatures that are trying to chase down the mammoth and outrun it and so on. But they are these bizarre, upright, walking, primate things that have spears and have weapons. And oh my God, and mammoths were smart animals. Elephants are some of the smartest mammals of all. And, the scene is basically that, this mammoth is used to being the smartest thing around, and now there's this new creature on the scene, being, of course, human beings, Homo sapiens. And really, it was probably, depending on the archaeological evidence, probably between about 15,000, maybe 25,000 years ago, that humans even came into North America for the first time. So really, like a scene when I was writing this, that mammoth, that might have been the first time a mammoth like that would have actually seen a human. They were such new predators, and mammoths did not evolve with humans. They didn't evolve alongside humans. They didn't learn our tricks. The African mammals did, the elephants there, and the, zebras and giraffes and so on. But a lot of the rest of the big mammals that were alive when humans started to spread around the world, they did not know humans. They were not used to humans. They had no defenses or few defenses against humans. And humans really did spread like a pandemic in many ways and wiped out a lot of these other mammals.
Steve, to zoom out a bit, just to look at the evolutionary process, one question that some people raise about it, I've interviewed a creationist, and he raised this thing, how is it that things seem to evolve when they're coordinated? It would seem that we'd have small evolutions and, things would happen piecemeal, and yet we get these amazing biological processes, these things that seem to work together so well. Does evolution happen piecemeal, or do some big things happen all at once?
Yeah. Probably both. I mean, a lot of evolution is piecemeal, small changes that happen generation by generation as individuals have to confront their own environment. That's what natural selection is all about. It's whether or not I'm going to leave offspring, personally, myself, and how many offspring I'm going to leave. And that all has to do with how well I can confront the challenges in front of me, whether it's from other animals, whether it's from the weather. And, you then multiply that over the course of countless generations, and that's how you get evolutionary change. But there are some times in history, in the fossil record, where we do see things change quite quickly, it seems like. And that might be because there's some sort of huge external force that's basically, changing things dramatically, like the asteroids, say, that wiped out the dinosaurs. That wouldn't have necessarily caused, evolution to speed up. I mean, maybe it, could have, but it would have put tremendous pressure on organisms, and it would have acted as a filter, basically. It would have just wiped a bunch of stuff away that couldn't deal with that asteroid and the fires and the earthquakes and so on in the then and now. So by and large, evolution is something that happens piecemeal over long periods of time, but sometimes things can happen quite dramatically. I think, though, we always have to remember that when we're looking at the history of life, we're looking at it from our vantage point. We're looking backwards at what has already happened. We're seeing basically the victors in that story, and we're interpreting it after the fact. And it's easy to put a narrative on something, to string out a story on something when you're looking at that evidence. But that doesn't mean that was inevitable, or it doesn't mean it was nice and clean. It certainly doesn't mean when we look at fossils and we see, some dinosaurs evolving feathers and so on, we're not seeing every step in that chain. We're seeing little snapshots of it. So, our understanding of evolution is pretty good, but is always going to have some gaps.
Just curious, have you ever seen any gaps that made you doubt it or heard a good argument for creationism?
No, not for creationism. I think, again, my view is that, the evidence for evolution is overwhelming. I mean, and it's not just fossils. We do have a great fossil record that, stretches back 4 billion years, basically. And, it's all pretty consistent. We don't find fossil humans with the first fossil bacteria. It's all pretty consistent. And we have a good way of dating rocks and, telling that story over time. But that's only a small snippet of the evidence for evolution. That's not what Darwin used to develop the idea of natural selection. It's about animals today. It's about how animals breed today. It's about looking at how animals develop from an embryo into an adult. It's about looking what happens in ecosystems as climate changes or a predator's introduced. There's all this overwhelming evidence for evolution. So evolution is a fact of life. It's one of the natural laws. It's like gravity. It's like electromagnetism. You can doubt it if you want. Sure. I mean, we all have free will. If you can doubt it if you want, but the evidence is overwhelming. What I think there's always room for is, spiritual interpretations or religious interpretations of humanity, of our own uniqueness. Yes, we physically came from other animals through this process of evolution. The evidence is there for that. So yeah, I mean, what's described in Genesis, like, no, that did not happen. We have fossils that tell us that didn't happen. Now, you can choose not to believe that. That's fine. But just because maybe that sequence of events in Genesis didn't happen, maybe just because, we did evolve from apes that evolved from other things that go back 4 billion years, that doesn't mean that you can completely eliminate any possibility for spirituality, for a higher power. I mean, ultimately, we're all here. The universe had to come from somewhere. Yeah. And for me personally, I have, lots of respect for the different traditions and different attempts that humans have made over the years to understand the greater picture, the bigger story of why we're here, the purpose in the world. So evolution can tell us, more or less the how that things happened. But there are great unanswered questions about the why and what it means and why we matter, why we're here. And I wrestle with those as well. I mean, I'm from a small town in the middle of the farm country. I'm from an Italian Catholic family. I've actually maintained many aspects of that faith. I believe things spiritually and religiously that I have no scientific proof for, that I would never even try to find. I'm not going to find a fossil of Jesus or something like that. I mean, that's just not how it works. It's a different way of thinking about the world. So, I try to avoid, debating creationists or getting into these kind of arguments. And I just try to say, look, we have all this evidence that evolution happens. It's one of the fundamental laws of our world. We have great fossil evidence of where we came from. We have all these human ancestors preserved, unless there is a trickster, demon god that is trying to mislead us. Like, all that evidence is there. But the way that we see ourselves in the grand story of life and the universe, well, leave room for what you want to leave room for.
Yeah, and that's a beautiful element to that consciousness thing that we've been talking about a little bit too, is our ability to kind of reflect on these bigger questions. And Steve, you mentioned Darwin. You are at the University of Edinburgh. He's perhaps your most famous dropout.
He is. And I talk about this in the mammal book. I love it. So, and I tell this to my students every year, the first year students, the freshmen, basically, we don't call them freshman year, but the first years that start. And I say, if you make it through to the end of your degree, you will have eclipsed Charles Darwin, because Darwin came to Edinburgh in the 1820s, and he was a very young man. I mean, he was, I can't remember when he started. He might have, he might have been 16 or 17. I can't remember. But he started a medical degree. And Edinburgh was really the center of the medical world then. You know, it was like the world's greatest medical school. And this was the time of the grave robbers, when those guys would go out and dig up corpses to sell to the medical school, because, you know, everybody wanted to study medicine, and it was just in the culture, in the air. A lot of the great advances of our understanding of the human body happened during that time, and Darwin was part of it. But he didn't want to be. His father wanted him to be a doctor. And Darwin did not want to be, but he obliged. His father, you know, was well connected. He got into Edinburgh to the top medical school, and he hated it. He hated his lectures. He thought his lectures were boring, were really dull. They probably were. And he hated blood. I mean, that's a problem if you're going to be a doctor, especially if you're going to be like a early 19th century doctor. And so he skipped class. And he would go out, he'd go along the coastline here, the Firth of Forth, which is the inlet of the North Sea that Edinburgh borders, just about a mile or so from where I am now. And Darwin would go out and he'd look at the creatures on at the seaside. He'd collect shells. He'd look in the tide pools, and he would spend a lot of time with one of his professors, this guy named Robert Grant, who wasn't a medical professor, you know, in that way, but he was a naturalist, and he was a radical naturalist. He was somebody who believed in evolution. Now, you might say, well, how could Darwin's teacher believe in evolution? Because Darwin hadn't come up with the theory yet. But what Darwin came up with was natural selection, the mechanism for how evolution works by survival of the fittest, basically. But when Darwin was studying, there was also this buzz in the air. A lot of people were starting to understand that life can change. And this guy Grant was, you know, one of these radical young professors. So Darwin took a great liking to him, spent a lot of time with Grant, collecting stuff by the seashore, not going to his lectures. That lasted 2 years. It was untenable. He dropped out. He quit. He certainly is our most famous dropout. Then, a little bit later, his dad got him a place at a much easier university, Cambridge. Got him a place at Cambridge. And a very different degree, a theology degree. And Darwin finished that degree, and he was destined really to become a small town, small county parson. You know, just, I mean, a wealthy one, because he had family money, but somebody who would just be the parson of an Anglican church, you know, somewhere in the English countryside. He didn't want that. So that's when he found the spot on the Beagle, on the ship that was sailing around the world. And for 5 years, he was on that ship. He was the naturalist on the ship. He put into practice a lot of what he learned here in Edinburgh, not in class, but from Robert Grant, in just collecting and identifying and studying and describing animals and plants and rocks and minerals. And those observations sailing around the world were the basis for his mechanism for evolution by natural selection.
Yeah. So the University of Edinburgh has this Darwin as the starting point of this idea. And then much later in the university's history, the cloning of Dolly. Yeah. I mean, where does that sit in the university? I mean, what that moment? I mean,
well,
what does it mean to you?
I'll tell you where Dolly actually sits now is in the National Museum of Scotland in town. One of the prize exhibits. You can go see Dolly. It's a great museum. It's our national museum, and it has all kinds of exhibits across the board, natural science and historical exhibits, and Dolly is really at the center. Dolly was cloned in 1997, I believe, and it was cloned right here at the Roslin Institute. That's one of our institutes here at the university that does a lot of genetics research. And Dolly was the first mammal that was cloned, and it wasn't that long ago. But I remember, I was 13 years old, I guess, then, and I remember the news, this huge news, a mammal's cloned, like this Xerox copy of this sheep has been made. Like, whoa, could humans do this? Should we? All the debate about that. But that happened here. We have world-class experts in genetics and in developmental biology, and so much of that early cloning technology was done here. And, I think it's cool. It's, for me, I mean, being part of a university like this, being on the faculty, it's really neat. It's great. It's to be, part of that legacy that's had such a deep legacy in science. This is also where the whole science of geology started, modern earth science. There's a guy, James Hutton, who was a University of Edinburgh graduate. He lived here in town. He did many things. He was a chemist for a while. He was a lawyer for a while. But what he ended up really doing was farming. He was a gentleman farmer. He had a lot of land, him and his family, they owned around here. And he observed on his land. This was in the late 1700s, Just how, erosion, wind, rain just constantly reshape that land, and it would wipe away sand and mud, and they would form, deposits that kind of look like rocks. And that just helped him reason out that the earth is old and that the processes that are happening today, whether it's wind and rain or whether it's volcanoes erupting or earthquakes or whatever, have over long stretches of time shaped the earth and have made mountains rise up and made seas change. And, up until that time, nobody had really articulated that. It seems obvious for us now, but until somebody put the pieces together, it wasn't obvious. And that happened here too. So there's a great, great legacy of history of science.
Yeah. And it seems that DNA is something that we're in a revolution with right now in terms of the understanding of it. How, if at all, does DNA play into your work, DNA science and things like that? We've talked a lot about fossils.
Mm-hmm. it does play a role. It is very hard, though, to get DNA to fossilize. DNA, it's just it's a chemical. I mean, really, it's just the little stuff that's inside your cells, and it breaks down really quickly once an organism dies. And the oldest DNA that's ever been found, as far as I know, is somewhere between like 1 and 1.5 million years old, something like that. And it's from mammoth bones that are from, I believe, from Siberia. I'd have to check the details. But they've been kept quite cool. There have been times where they've been frozen and so on, and that's probably helped them be preserved. But DNA is hard to preserve. Nobody's ever found any dinosaur DNA. The dinosaurs like T-Rex and Triceratops, they went extinct 66 million years ago, a long time ago. No DNA even close to that age has ever been found. So probably the movies, will not happen. I don't want to, never say never as a scientist, but it would be very unlikely for some T-Rex DNA to be found. But it does mean that if you study animals that have more recent fossil ancestors, like, say, woolly mammoths and stuff, you can use DNA. And so that means that for some of the work we do on mammals, actually, we do use DNA of modern mammals and the limited fossil DNA we have to help build the family trees, to slot the fossils into the family trees. And it's especially helpful if you maybe have a little bit of DNA from some fossil, and then you have maybe a bunch of older fossils that you'll never get DNA from, probably. But if you have that tie point of the DNA from a relatively recent one where a bit is still preserved, that can help you just fill out the family tree and help you figure out what those older fossils are related to. So we do this kind of work with mammals. We have a big project in my lab now that we've been working on for quite a while on building a family tree of basically the mammals that survived the dinosaur extinction and then laid the foundation for the modern world.
Mm-hmm. So we have this DNA now of the woolly mammoth. So you said maybe we don't get Jurassic Park anytime in the future. What hope is there for bringing back the woolly mammoth?
Well, the woolly mammoth is something that died quite recently. I mean, basically, they lived up until about 10,000 years ago, but some survived on islands until, for a few thousand years after that. So the woolly mammoth was around. There were still mammoths, like when the pyramids were being built and stuff. I mean, they were on their way out, but they were still there. So we know the entire genome of the woolly mammoth. I mean, the whole genome has been sequenced. We know more about mammoth genetics than we do about the genetics of a lot of modern day animals. So that information is there. I mean, the tricky thing is, how you would grow a mammoth. Yeah, all the DNA code, but, what's the mother going to be and how's that pregnancy going to work? Then, of course, if one is, born, what do you do with it? Where do you put it? The environment mammoths lived in isn't really around much anymore because the world has changed and the climate's changed so quickly since then. But it's something that, I mean, far from my expertise, but it seems like it's something that's at least within the realm of possibilities. And, whether we should do it, that's another question, the ethics of it. And that's, I have lots of views there that, I could explore the pros and cons, but I would just say I'm no, ethicist. I'm not going to pretend to speak for everybody, but I would just say I'd have some pretty serious concerns about bringing back something that's been extinct for a while into a world that's very different than the world it grew up in. At the same time, for woolly mammoths, I mean, we are almost certainly the reason why they're not here anymore. They went extinct because of humans hunting them and changing their environment and so on. So it would be a little bit different than bringing back a T-Rex, at least ethically. I mean, a T-Rex, lived long before humans. We had nothing to do with the asteroid that killed it. But the mammoth, it's kind of our fault. So could we rectify that? Could we get penance for our sins there as a species? Then you're getting deep into the ethics. And then, people get are very opinionated about this. And I don't actually have a firm opinion other than just be very careful when it comes to bringing back extinct species. Not because they're going to overrun the earth and cause chaos, like the Jurassic World dinosaurs, but because it might just be unbelievably cruel to bring them back, into this world, a world that they didn't know, and a world where there's so many endangered species that we should really be focusing on conserving and saving rather than, bringing back something that's already gone. If we could do those things at the same time, maybe great, but that's just not usually how human nature works, and certainly not how funding for science works. And, one of my concerns is that this rush to do de-extinction, as bold and bombastic in a good way, as a scientific challenge, that it is, that might suck away a lot of the resources and a lot of the bandwidth, a lot of our attention from conserving the many, 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 many endangered, mammals that are still with us, but might not be if we do not make a concerted effort to conserve them.
Mm-hmm. And ethics aside, just for fun, how would it work? Do you breed the woolly mammoth with a modern day elephant?
I don't know. This is where I'm not a geneticist. I don't know. I mean, I know it's a challenge. If it was easy, it would have been done by now, especially since we have, the whole genome. I know there's many eminent geneticists that are working on this. And yeah, that would generally be, the gist of it, I think, is having a modern, elephant as the host, as the mother. But of course, a mammoth is a different species. So, getting one species to give birth to another, I mean, I can only imagine the challenges there.
Mm-hmm. Well, Steve Brusatte, before we get to our last topic, for people who want to find out more from you, where should they look for you online?
So, I mean, I'm pretty active on social media. You can see me on Instagram, on, Twitter, X, on Blue Sky as well. I don't do TikTok. I'm too old for that. And for, I don't want, the people that own TikTok to have all my data. So I'm on social media. I mean, you can, check out my university website. A lot of my academic publications are there. And, there's a lot of YouTube videos of lectures I've done and talks I've given and, other podcasts and stuff. And that's probably the best place to find me. But the books that I've done, The Rise and Fall of the Dinosaurs and The Rise and Reign of the Mammals, those are pop science books that are for general, broad audiences. Yes, thank you. Look for that beautiful cover by Todd Marshall, one of the great artists who does fossil art. But those books are the best way to, get a feel for my view of the world and my approach to studying evolution. And then I'll have the new one on birds coming out. It's called The Story of Birds, and it will come out sometime between April and June 2026, just, nailing down the exact date. But that will tell the story of how birds evolved from dinosaurs, how these fierce meat-eating, ground-living dinosaurs developed feathers and elaborated those into wings and took to the skies, and how they survived the asteroid that killed off all the other dinosaurs and then produced the birds of today, all the magnificent birds that we have around us. So that's what I've been working on. And otherwise, I pop up here and there, and good podcasts everywhere.
Great. Well, we'll put some links in the description for people to check you out. Right. And see, my last topic is really you. You have this cool job, and I think a lot of us, we get the idea of a paleontologist from the movies, and yet you shape the movies. I mean, what is it like to do this work and to have sort of this scientist dream job?
I do shape the movie. That's why Jonathan Bailey's playing the paleontologist, because he looks so much like me physically. And no, I do think in the latest film, he does play the paleontologist, and he does a great job at it. He really captures, I think, the essence of being a scientist who studies the history of life and evolution, and has that deep respect and awe and admiration for the natural world. Sam Neill's character in Jurassic Park is great too, the Alan Grant character. Ross from Friends is a pathetic character. Don't think, there's nothing paleontologist about that character. It's just a throwaway job. But the job I do is great. I love doing it. It's really varied. Of course, primarily I'm a researcher. I'm out looking for new fossils, discovering new fossils, and learning new things, whether it's in the field, whether it's in the lab. But a big part of my job is also teaching. I teach a lot of undergraduate courses. I mentor graduate students. And then I do, a lot of science communication, a lot of outreach, whether it's writing, whether it's working in the films, whether it's doing chats like these. I love that, just getting out of the university and talking science. And I can't think of anything better. Ultimately, every day when I get up, I have the opportunity to learn something new about the world, to discover something new, as every scientist does. That's a perk of just being a scientist. But for paleontology, if we're out looking for fossils, that's even bigger perk. Goodness knows what we can find. And then I also get a chance to talk about it and just revel in the passion and enthusiasm and wonder that I have for this field that I found when I was a teenager, that I just, became addicted to, because it's so cool. This is the history of Earth. These are T-Rexes and saber-toothed tigers and woolly mammoths, and come on. So I feel very fortunate, and I'm glad I get to work here, in Edinburgh. It's taken me a long way from home, but I get great students here. And my students find the most fantastic fossils. They come up with, greatest ideas. And it's really a nice way to make your way through life. So I feel very lucky.
Yeah, you have stories of like young undergraduates who are
Mhm.
finding these ancient
Yeah,
fossils, right?
yeah. I mean, it just a few months ago, my student Millie Mead, who's just started her second year of PhD here, studying brains and the evolution of cognition over time. She was out with us on the Isle of Skye in Scotland. This is looking in Jurassic age rocks, about 170 million years old. And, we have dinosaurs and pterodactyls there, but she found this beautiful, skeleton of an ichthyosaur. This is one of these ocean reptiles that lived with the dinosaurs, with the big long snout of gnarly teeth. And, that was her first trip with us, and she found it. I mean, incredible, right? I mean, you don't have to be a professor to find a fossil. You don't need to have a PhD. As long as you have the enthusiasm, as long as you have the patience to go out and look, um, anybody can find stuff. And that's the great thing. Paleontology is a very populist science, a very democratic science in that way. And I'm lucky that I have students that do this. I take them out. I don't have to find the good stuff. They can do it for me.
Well, Steve Brusatte, for the work that you do, for the inspiration that I'm sure you are to a lot of people, for this beautiful book, and
Thank you.
I mean, the cover is just the beginning,
Yeah.
and for taking this interview with me. Thank you so much.
Thank you, Brad. Appreciate it. And keep in touch. And maybe we'll talk again about birds.